This is lecture number 8 of the series of lectures on electric machine design. We will continue our discussion about design of transformers, and we will start with some recap of what we did in the last lecture. If you remember, we derived output equations for core and shell type single phase transformers, and this is the equation that we had derived in the last class. Q, which is the output of the transformer in kVA, is equal to 2.22 FBM delta kW AW AI into 10 to the power 3. So these equations hold for the core and the shell type transformer. In today's lecture, we will talk about the output equation of three-phase transformers. So let's start right away. You know that the output output Q in terms of kVA of a three-phase transformer is 3V phase I phase into 10 to the power minus 3, or you can also write this as 3Vs into Is into 10 to the power minus 3. This is approximately equal to 3 EP into 10 to the power minus 3. Since the applied voltage is almost equal to the induced voltage EP, and you can also write that this is approximately equal to 3 ES IS into 10 to the power minus 3, since the secondary voltage is also almost equal to the induced voltage in the secondary. The suffix P refers to primary, suffix S refers to secondary, V and E are the voltages, and I is the current. Right? These symbols carry the usual meanings. Now, if you see the core of a three-phase transformer, of a core type transformer, I'll draw it for you here. It has two windows. Draw this again. Okay, this is the height HW of the window. This is the width of the window, and the window area is AW. This is symmetric, so both windows have the same area. The area of the iron or the core is AI, like in case of single phase transformers, right? So this is the cross-sectional view of a three-phase core type transformer. And if you go on to see the winding arrangement, you see that the winding arrangement is something like this. The winding arrangement is something like this. So you have the LV, this is the HV, this is the LV for the second leg, this is the HV for the second leg, this is the LV, this is the LV, and this is the HV, and this is the HV. So you have area 1 and area 2, which is the cross section area of the conductor in the LV and the HV windings respectively. So this is the winding arrangement. Okay, so you have to remember that in each leg, that is this part is known as the leg of the transformer. This is one leg, this is second leg, and this is the third leg. So each winding, each leg has both primary and secondary windings of one phase. So if this is one leg of the transformer, this has primary and secondary winding of, say, phase A, right? This is phase B and this is phase C, right? So in each window, if you see that this is the window, right? This is the window. You have two primary and two secondary windings, right? So if you recall from the previous discussion about copper area, what should copper area be in this case? AC is equal to twice TPAP plus twice TSIS, isn't it? Double than what the area was in case of the single phase transformer, because that had one window only. Here we have two windows, right? So each window has double the number of windings. Okay, so this copper area refers to the copper area of each window. You have to make a note of it, that this copper area refers to the copper area of each window. Then if you follow the previous derivations of the single phase transformer, you will see that this AC can be manipulated and written as this. It's 2 times TP IP upon delta plus 2 TS IS upon delta, which then can be written as 2 over delta TP IP plus TS IS. Okay. So the copper area, if you substitute the MMF and the current for the, in place of, if you substitute the AMF AT for the currents, you can see that the copper area comes out to be, so it comes out to be 480 upon delta, right? And also if you recollect from the previous lecture, we derived the following expression, right? So this holds for the three-phase case, so it is delta KWAW upon 4. If you see the output 3, it is for the three-phase transformer, it is, and then we had introduced this term ET times TP IP into 10 to the power minus 3, which then was replaced by 80 into 10 to the power minus 3, which then can be written as 3 over delta kWAW by 4 into 10 to the power minus 3. And if you go back to the equation of voltage per turn, you see that, which was the equation, that 4.445 FB, the equation that we had derived earlier, 4.44 Fi, what was that equation? I'll go back to that equation. This equation, right? So this Ex by Tx is Et, so we will use this equation here, and what are we left with? We are left with 3 into 4.44 into F into phi m into delta kWAW by 4 into 10 to the power minus 3. So this comes out to be equal to 3.33 F phi m in delta kWAW into 10 to the power minus 3. And if you substitute phi m equal to Bm into Ai, the final equation is Q is equal to 3.33 F Bm delta kWAW Ai into 10 to the power minus 3. This is the output equation for a three-phase core-type transformer, where the symbols have their usual meanings. Okay. So this is the equation for the voltage, the output of a three-phase core-type transformer. This is three-phase core-type transformer. All right. Next, we talk about the three-phase shell-type transformer. So if you see the three-phase shell-type transformer, the winding in the cross-section looks something like this. My drawing is not very good, but when you draw it, you have to understand these are all symmetric, right? So this is equal to this, this window is equal to this window, and all of the windows are of the same dimensions. This is HW, this is WW, right? This is HW again, this is WW, right? HW, this is WW, right? So all of the windows are of the same size and have the area AW. Okay, and if you see the winding arrangement, something like this. If this is the core, you have the LV winding here. This is LV, this is HV, this is HV, this is HV, this is LV, this is HV, this is LV. And if you were to see the cross section, I mean the area, this looks something like this, right? So this is area 1 and area 2, like we had discussed in the last slide. Okay, this is LV, this is HV, and I forgot to mention here that this is iron area, AI, iron area, AI. So the point to note here is that there are 6 windows in this shell type transformer, and each window has LV and HV windings of one phase only, right? So you have, if this is window 1, 2, 1 and 2 will carry the LV and HV winding of phase A, 3 and 4 will carry the windings of phase B, 5 and 6 will carry the windings of phase C. Okay. So the copper area AC is given by TPAP plus TS into AS. Copper area in each window is given by AC equals to TPAP plus TSAS. And we follow the same steps which we followed in the derivation for the single phase and the 3-phase cases. So we will write this as IP over delta TS IS over delta, so which is equal to delta TP times IP plus TS times IS. Right, and if you substitute this TP IP with AT, which is the ampere turns or the MMF, you are left with 280 over delta. This 280 over delta, you know that it is equal to kWAW from the previous derivations. So this 80 can be written as delta kWAW by 2 . Okay. And we know that the power in a 3-phase core or shell type transformer is given by 3 EPIP into 10 to the power minus 3, and then we replace this EP by E T into TP into IP into 10 to the power minus 3, and then we write 3 ET times AT times 10 to the power minus 3, where TPIP is replaced by the ampere turns, and then we write 3 ET times delta KW AW by 2 into 10 to the power minus 3, and then when we manipulate this ET and substitute it with 4.44 F5, so what are we left with? We are left with 3 into 4.44 F5M into delta KW AW by 2 into 10 to the power minus 3, which is equal to 6.66 F5M F5M delta KW AW into 10 to the power minus 3. And if you substitute phi m with Bm into Ai, which is the iron area, we come up with this equation 6.66 F phi m, not phi m but F Bm delta KW AW AI into 10 to the power minus 3. So this is the output equation for a three-phase shell type transformer. Output equation for a three-phase shell type transformer. And if you notice that it is twice as compared to the core type transformer. So it is, the factor is 6.66 over here. In the core type transformer it was 3.33 only. Okay. Now that we have derived the output equations for all the cases of the transformers, we talk about voltage per turn of the winding. Q in kVA is written as V into I into 10 to the power minus 3, right? So this V we can replace with 4.44 F phi m into T into I into 10 to the power minus 3. So this is 4.44 F phi m A T into 10 to the power minus 3, right? We replace this Ti with equal to AT, right? So in this expression, phi m is known as the magnetic loading, and this AT, the MMF, is known as the electric loading. Electric loading. Fine. This is known to us. So what do we derive from this? What insight do we gain from this? this phi m, or the magnetic loading, is equal to the flux density times the area of iron, right? So it is, if you increase the magnetic loading, what is a consequence? Your Bm increases and Ai increases. What happens as a consequence? Core loss increases. What is the consequence of the core loss increase? Efficiency decreases. Alright, efficiency of operation decreases when you increase magnetic loading. On the other hand, AT is the electric loading, so it gives you a measure of the cross section of the winding. So if you have increase in electric loading, what happens? The number of turns increases. What happens? The resistance increases, and as a result, copper loss increases, which results to efficiency decrease. Okay. So if you have higher values of phi m and AT, these are responsible for decrease in efficiency. So for economic design, this ratio of phi m to AT is kept constant, and this ratio depends on the type of the transformer. What do I mean by that? I say that I call this ratio X. X is the ratio of the magnetic loading to the electric loading, and the electric loading is magnetic loading divided by X. So if you substitute AT from this equation in this equation, what do we get? We get Q is equal to 4.44 F phi m square by X into 10 to the power minus 3, and phi m is then written as square root of X into 10 to the power 3 divided by 4.44 F and into square root of Q. Okay, so this phi m is the square root of X into 10 to the power 3 divided by 4.44 F times square root of Q. So the volt per turn of the winding is given by ET is equal to 4.44 F phi m So we are going to substitute the value of phi m from the previous expression into square root of q. So we are left with this expression 4.44 f into x into 10 to the power 3 into square root of q. So ET is equal to k times square root of q, where k is equal to square root of 4.44 f x into 10 to the power 3. So therefore x, which is the ratio of 80 and the ratio of phi to 80, and this k, these are constants, and these parameters, these constants, depend on the type. I should write that they are constants, and value depends on type, construction, and service conditions of the transformer. So I have a little bit of information for you. If you have a single phase core type transformer, the value of this k ranges from 0.75 to 0.85. Three phase core and power transformer, this value is between 0.6 to 0.7. Three phase core distribution, the value is 0.45. Single phase shell, it is 1 to 1.2, and if you have a three phase shell, the value is 1.3. So these are typical values of this constant k, depending on the type, construction, and nature of service that the transformer provides. Is this okay? Before we conclude this lecture, I would like to mention about choice of flux density. The flux density, as you must have seen in the previous equations, this flux density Bm affects the iron area or the core area Ai, right? And for the same flux, you can see from this equation, for the same flux, a higher flux density leads to lower area, right? So what happens, let me shift this to the next page. Choice of flux density. So if you have Bm affects the core area Ai, right? If you have a higher flux density, core area is reduced, So what happens if the core area is reduced? This reduces the diameter of circumscribing circle, which is the diameter of the circle circumscribed in by the, I mean the core has a circumscribing circle defined over it, and if this dia is reduced, what happens? The mean length of the mean turn of the winding is reduced. This also we discussed in the previous lectures. So if the mean length of the mean turn of the winding is reduced, LMT, let me write it here, length of mean turn of the winding. So this gets reduced. What will happen as a result? There will be saving in terms of copper. Lesser copper will be used and lesser iron will be used, right? However, you cannot simply go on increasing this flux density, because a higher flux density leads to an increased magnetizing current. Let me write however here. In increasing BM leads to increased magnetizing current IM, which may ultimately lead to saturation, and this is a condition that we would like to avoid, right? So for distribution type transformers, so for this BM, the choice of this BM also depends on the type and service conditions of the transformer. So if you see that you have distribution transformers, they are designed for low iron losses, and they give good all day efficiency, right? Hence, for these distribution transformers, this BM can be lower. And again, we have some data that typically this must be the distribution of the flux density type, and then we have BM on the right hand side. It is distribution transformer hot rolled steel. The value of BM is 1.1 to 1.4 Weber per meter square. For power transformers, again hot rolled steel, it is 1.2 to 1.5 Weber per meter square. Then transformer using cold rolled grain oriented steel, there are 3 types. Let me just extend this here. Up to 132 kV, you have 1.55 Weber per meter square. Around 275 kV, it is 1.6, and about 400 kV it is 1.7 Weber per meter square. Okay, so this is the data on typical values of flux density Bm. Then we have to discuss about choice of current density delta. So this delta depends on the electric loading, right? Since this is related to current, so depending on the nature of the load or the electric loading, delta is, what is delta? Delta is current over area, right? Current per unit area. So if you have a higher value of current density, that means you will have smaller dimensions of the transformer, right? Smaller dimensions of the transformer, a higher value, higher delta means size of the transformer is reduced. But is that very good or very bad? Let's see. But if you have higher loading or higher delta, you have heating issues are there, you have losses, right? You have efficiency, you can see that efficiency is decreasing because of these heat and these unnecessary losses. And with this heating, what happens is that this can lead to damage to the insulation, right? So we would want to avoid that. So you would want to have improved methods of cooling. Improved methods of cooling would be required to cool transformers with higher current densities. So again we have a table. You have standard distribution transformer and small power transformer. They have the value between 1.5 to 2.6 ampere per mm square. Then you have medium to large power transformers. It is around 2.4 to 3.4 ampere per mm square. And for large power transformers, it is about 5.4 to 6.3 ampere per mm square. So this was all about today's lecture. I will conclude now. So in today's lecture, we talked about the output equation for three-phase core and shell type transformers. We then talked about choice of flux density, and we talked about voltage per turn of the winding, and then we also talked about choice of current density. So with this we conclude this lecture, and in the next lecture we will proceed further and continue this discussion, and we will talk about the design of the core and the winding and the overall design of